All right, ladies and gentlemen, good afternoon or good morning. We're here with my period 6 class. Say hello, period 6. Hi. Okay, so we're going to be, hopefully now, this will work. So we're going to go over questions 17 through 28 on the review sheet. So let me get over here to 17. Zoom out so we can see most of it. So question number 17. And it looks like somehow I started annotating this. When you're taking your test this time, you're going to get 10 free points for just annotating, for showing me your work. If you're doing a problem here and you're saying, hey, the temperature is increasing by, the pressure is going up by 2, that's what I mean by annotating. You can get 10 free points. If you don't, you're not going to get 10 points. So you need to make sure to annotate and show your work on our test. So a gas occupies this volume, which I've got labeled here as volume 1. At this pressure in kilopascals. So I'm going to label that, that's already labeled pressure 1. I recommend that you do this when you're working on these. What volume? So now you're looking for volume 2. So that's going to be what we're going to be calculating in this. And let's see, what volume will the gas occupy at this new pressure of 80 kilopascals? That's pressure 2. Now earlier, since we're working with volume and pressure, that's going to be Boyle's law, which we've already gone over in the first video. And so that's the equation we're going to be using. It's really nice that we don't have to cross multiply it. So I'm going to write down the base equation. Pressure 1, volume 1 equals pressure 2, volume 2. We are trying to find volume 2. So we got to divide both sides by pressure 2 in order to cancel this out over here. Now when we go to set up this problem and solve it, pressure 1 is 12.3 kilopascals. We got to multiply it by the starting volume of 3 liters. And now we got to divide it by pressure 2 of 80 kilopascals. Hey, ladies and gentlemen out there, this is a live recording here, so I do need you to be courteous there. And if you don't want to follow, then you just need to quietly be reviewing over there. Now, we're going from 12 to 80 kilopascals. So our pressure is increasing. What are we going to expect our volume to do? Are they directly or inversely proportional? What are they? Pressure and volume. Period 6, directly or inversely related? They're inversely. So we should expect, if the pressure goes up, as it did in this problem, you should expect volume 2 to be smaller than 3 liters. Now you can do the math yourself. I'm not going to do that here. Question number 18. Gas has a temperature of 30 degrees. This is temperature 1. And we need to add 273 to this. And can you help me out? What is 273 plus 30? What did you all get that did this problem? Come on, period 6, wake up out there. 303, okay, that sounds about right. 303 Kelvin. It's only on the gas laws. You have to change the Kelvin. You don't have to do that if we're doing MCAT or other things with heat problems. And this is temperature 1 right here, 800 kilopascals. The problem is asking what temperature. That's going to be temperature 2 is what we're looking for. And it's telling us the pressure is dropping to this new pressure. Now, if pressure drops, is pressure and temperature, are they directly or inversely proportional to each other? What is it, period 6? They're directly. Anytime you have temperature, they are directly proportional. Put the capital T there. They're directly proportional. So if the pressure's dropping, you should expect temperature 2, the new pressure, is going to be less than 303. So now this is temperature and pressure. That was Gay-Lussac's law. And these will be provided for you, but you have to remember how to cross multiply these so that you're ready to rearrange the solve for a particular problem. So I'm going to put pressure 1, temperature 2 will be equal to pressure 2, temperature 1. That's the problem rearranged. Since we're looking for temperature 2, we've got to divide both sides of the equation by P1. It'll cancel on this side. And we're going to substitute in pressure 2 is 350 kilopascals. You got to multiply it by the starting temperature, which you all said was 303 kelvins. And we got to divide that by our starting pressure, which we said was over here was 800. Now this is where you got to be real careful, because sometimes depending upon how you set up these problems, you might accidentally get the pressures mixed up. Make sure pressure 1, this is the first pressure they gave us in kilopascals. And you know what? Right here, I can cancel that kilopascal with that one. I know I set it up right and that I don't have to change one of these. And now when you do the math, 350 times 303 divided by 800, you'll get your answer, which should be less than 303 kelvins. Number 19, you've got a sample of gas with this volume, so label that volume 1. We're at negative 100 degrees Celsius. This is temperature 2. Excuse me, sorry, temperature 1, my mistake. So we got to change that to kelvins. So in the calculator, I'm going to put in 100 degrees. And if you don't know, on your scientific calculators, they usually have a change of sign. It looks like a plus minus. So you can enter in that, hit the button. Now I've got negative 100 on there. And then we're just going to add 273 to that. Now some of you may have done that in your head. Okay. 173 kelvins is going to be our temperature 1 that we need to work with. We're looking for volume. What volume? So you're looking for volume 2 is what we're going to have to solve for. And we're going to have to add 273. Help me out there. What is 273 plus 65, period 6? How many kelvins does that come out to be? Nobody did this problem? Nobody can tell me right now what your kelvins were down here? Okay, what's 5 plus 3? 338. Okay, 338. That agrees. Yeah, okay, I agree with that. And this is temperature 2. Now, this is temperature and volume. This is our friend Charles's law. And Charles's law is set up first as a fraction. I would recommend you cross-multiply it so that you're ready to isolate for any variable you need. So that's going to be V1 times T2. V1 times T2 is going to be equal to volume 2 times temperature 1, and we're looking for volume 2. So we've got to get rid of temperature 1 over here. We need V2 all by itself. That'll cancel out. So when you go to substitute in, we're going to put the starting volume, 20 liters. We're going to multiply that. Now here's, be careful, we need temperature 2. So here's temperature 2, 338 kelvins. And we're going to divide it by temperature 1, the 173. Now we're going from like negative 100 degrees Celsius to 65. The temperature is increasing. So what will we expect volume? Are they directly proportional or inversely proportional to each other? Well, what is it, class? Temperature and volume, directly proportional or inversely? That's going to be directly. So we should expect that the volume should be bigger than what we started with. Your answer should be bigger than 20. Actually, if you kind of realize that the volume has to be bigger than what we started with, if there's only one answer that's bigger than 20, you don't even have to do the calculation. So sometimes that'll happen. You'll get lucky and that'll happen. Okay, number 20 on the back page here. A piece of metal is heated and then it's submerged in cool water. Okay, so this is hot. And then it's submerged in cool. This is cool. Okay, probably sizzling and stuff will happen when that happens. Like, did you get a? I think you got a sizzling when you put your conduction probes into the water when we were done. Did you get some sizzling there? Anyway, what will happen to the temperature of the water? So you put this hot metal in cool water. What happens to the temperature of the water? Is it going to go up or go down? Period 6. What's going to happen? What's the temperature of the water going to do if you shove a hot piece of metal into it? The temperature of water is going to get hotter. I don't know if that's proper English. You can ask your English teacher. Get hotter. Next question. What happens to the temperature of the metal? T metal. Is the metal going to get hotter or cooler? Ladies and gentlemen, what's going to happen? You put that hot metal in cold water, what's going to happen to the metal? It's definitely going to get cooler. So gets cooler. Maybe I should put the S's on those. There we go. And lastly, how does this show that heat energy is conserved? It's not created or destroyed. Well, what's happening is this heat is being transferred to where it's cool. And that's what heat is, the flow from high kinetic energy to low kinetic energy. So it's the temperature drop of the metal in calories should equal the temperature rise in calories. Actually, I should say the heat loss here in calories will equal the heat gain there. Number 21 has a mistake on it. It doesn't make sense the way it is. You need to cross off system and write surroundings, please. So let's get that done. Once you do that, it'll start to make sense. If heat is released by a chemical system, okay, you've got a system, heat's coming out of it. And if it leaves the system, where does the heat have to go if it leaves the system? What's the other part of the universe? It's the surroundings, okay. So if you release some heat from the system, it's an equal amount of heat will be gained by the surroundings. Gained by, and that was in our lab we were working with today with the heat of fusion. The amount of heat that is lost by the water was gained by the ice cube to melt it. Endothermic reaction. So endothermic, you've got the system. Is energy exiting or entering the system if it's endothermic? Energy's entering. I'm just going to put an E going in. Will Q be plus or negative? Is this a plus interaction if you're adding energy to the system, or a negative? Q will be plus. If a delta T, if this was other than a phase change, the delta T would also be plus. So exothermic must just be the opposite. We've got the system, and we've got energy is exiting the system. It exits, energy exits. And so since we're subtracting heat energy, Q will be negative, just the opposite of that one. And if there is a delta T involved, it will also be negative, which means the thing's getting colder. You're pulling heat out. Little conversion factor here to do for number 23. We're given 127 little c calories. We'll put that over 1 as we do any conversion. And then we've got to multiply that by a fraction in such a way that the calories, we can diagonally cancel those out. So let's see, 1 calorie for every 4.18 joules. If I could cancel right there, you set this up right, and you should probably have a number. It's probably about 500 or something when you actually calculate it. Number 24, what's the equation for delta T? It's delta T is going to equal a temperature minus a temperature, and my memory clue is that you think of this is the first temperature and that's the second temperature. That's just a memory clue. Actually, the F stands for final temperature and the S is for starting. So you can use the memory clue first and second. I do that to this day. I've done it for 40 years. Works for me. Maybe you've got something. So now let's do number 25. If 90-degree water cools, okay, this is temperature starting, to negative 20, that's temperature final. We said delta T is going to be the temperature starting minus, my mistake, first and second. There we go. Final temperature. So we're going to have negative 20 is the final temperature minus 90 degrees. That should be Celsius. There we go. And we're going to have, like, what is that going to be, negative 110 or something like that. But it's going to be negative because we're cooling it down. This problem over here, we have 10-degree water. This is temperature starting. This is our final temperature of 90 degrees, temperature final. Delta T. Now, you know what? I don't think we have the equation for delta T. So that might be something you're going to have to make sure you remember, that delta T is the temperature minus, and I use my memory clue, first and second, final minus starting. And if you label these, temperature F is 90 degrees Celsius minus 10 degrees Celsius, and you'll get an answer that's going to be, it's going to be a plus answer. Let me do that one so you can do that yourselves. Okay, the last couple here, and then we'll, in this problem, number 27, what is the amount of heat, that's Q, required to raise the temperature? Now we're raising the temperature. That means it's going to be a plus delta T by 15 degrees. So delta T is 15 degrees, but it'll be plus because we're making it hotter. 300 is our mass. So since we have a delta T, and if you forget, on your chart that you'll be given, you've got, if there's no phase change, if we have a delta T, it's the MCAT equation. Q will be equal to the mass times C times delta T. And in this problem, we've got 300 grams times, we'll always give you the specific heat, 0.21 calories over gram degree Celsius. And then we got to multiply it by the delta T, and that's plus 15 degrees Celsius. Then you could do the math right there. The last problem, we're going to set it up the same. It is just like this one. It's Q equals M times C times delta T. We're looking for how many calories. That's Q. This is our mass. Now we're going from 300 temperature starting to our final temperature, temperature F. So let's see, delta T will be temperature final minus temperature starting, which will be 56 minus 300. Okay, I need some help there. What's 56 minus 300? Somebody got that one already? Well, look at there. We're almost done here with the period. It's negative. Did anybody get negative 244 for your delta T on this one? Okay, got a couple people. So negative 244 degrees Celsius. So now to solve the problem, mass is 325 grams. Specific heat is still 0.2 calories over gram degrees Celsius. And we still have, our delta T is now, wow, that's a big delta T. Negative 244. Hopefully I did that correctly. Okay. And then multiply those out, because this is getting cool. Thank you for your attention, period 6. You can pack up now.